Hello and welcome. Today, we're diving deep into Advanced Kubernetes Operator Patterns, a critical topic for anyone looking to master modern cloud-native deployments. By the end of this lesson, you won't just understand these concepts, you'll be equipped to apply them in your own systems. Our journey will cover several key areas. First, you'll learn to create custom Kubernetes operators to automate complex application lifecycles. This is about making Kubernetes work for your specific needs, not just generic deployments. Second, we'll explore how to implement advanced pod scheduling using powerful tools like affinity rules and disruption budgets, ensuring your applications are always where they need to be and always available. Third, you'll discover how to build robust resource management systems with quotas and capacity planning, preventing resource starvation and optimizing cluster utilization. Finally, we'll discuss how to deploy monitoring dashboards to visualize operator behavior, giving you real-time insights into your automated systems. This lesson is designed to give you practical, actionable knowledge to build more resilient, scalable, and self-healing applications. Let's start with the foundational concepts that power advanced Kubernetes automation: custom resource definitions, or CRDs, and the operator pattern. Think of CRDs as your way to extend the Kubernetes API itself. Instead of just using built-in resource types like pods or deployments, CRDs let you define your own application types, like a web app or database resource. These custom resources act as blueprints, specifying exactly how your application should look and behave. When you create a web app resource, Kubernetes understands it because of your CRD. This brings us to the operator pattern. Operators are essentially Kubernetes on autopilot. They're specialized controllers that constantly watch for changes to your custom resources. When an operator detects a change, say you've requested a new web app, it automatically takes action to reconcile the desired state with the actual state of your cluster. This means creating, updating, or deleting underlying Kubernetes resources like deployments, services, and ingresses, all without manual intervention. This powerful control loop is what allows systems like Netflix to manage hundreds of microservices with incredible efficiency, encoding operational knowledge directly into code. Now, let's zoom out and look at the typical system architecture and control flow when using advanced Kubernetes patterns. Our advanced system usually comprises three main layers. First, the custom resource layer, which is where you define your application specifications using CRDs, essentially telling Kubernetes what you want. Second, we have the controller layer. This is typically a Python-based operator or similar that manages the resource lifecycles. It's the how, taking your specifications and making them a reality in the cluster. And finally, the scheduling layer, which handles advanced pod placement using rules like affinity and anti-affinity, ensuring pods land on the right nodes and always available. The core of the operator's work is its reconciliation loop, driven by state transitions. An application might move from pending to creating, then to running, updating, scaling, or terminating. Each of these transitions triggers specific actions from your operator. If a state transition fails, the operator is smart enough to automatically trigger retry mechanisms, often with exponential backoff, to ensure resilience. This continuous event-driven cycle ensures your applications remain in their desired state, even as the environment changes. Beyond basic deployments, advanced Kubernetes patterns offer sophisticated tools for scheduling and resource management, critical for robust production systems. First, let's talk about pod disruption budgets, or PDBs. These are your safety net for high availability during planned cluster maintenance. PDBs specify the minimum number of available replicas for a service during voluntary disruptions like node upgrades. For example, you might set a PDB to ensure that at least 50% of your critical service replicas are always running, preventing downtime. Next, node affinity provides intelligent pod placement. You can define rules to place pods on specific nodes based on labels, optimizing resource utilization or meeting compliance requirements. This includes both required rules for hard constraints, like ensuring a database only runs on a specific type of instance, and preferred rules for optimization, such as spreading pods across different availability zones to enhance fault tolerance. Finally, resource quotas and capacity planning are vital. Namespace-level resource quotas prevent individual teams or applications from monopolizing cluster resources. By integrating capacity planning, your operator can monitor utilization trends, predict future needs, and even automatically suggest quota adjustments, ensuring efficient resource allocation and preventing resource starvation. Bringing these patterns to production requires careful consideration of high availability, monitoring, and security. For high availability, deploy your operator with multiple replicas, spreading them across different availability zones to prevent single points of failure. Implement leader election to ensure that only one operator is active at a time, avoiding conflicts. And crucially, ensure graceful shutdown handling to prevent resource leaks during termination. Next, monitoring and observability are non-negotiable. Integrate Prometheus metrics into your operator to expose performance, resource utilization, and reconciliation success rates. Custom dashboards provide real-time visibility, allowing you to quickly spot issues and ensure your automated systems are behaving as expected. And finally, security considerations are paramount. Always apply the principle of least privilege with RBAC integration for your operator's service accounts. Security manage sensitive configuration data through secret management solutions. And implement strict network policies to restrict operator communication to only essential services, minimizing the attack surface. By applying these advanced Kubernetes operator patterns, you can build highly reliable, scalable, and self-healing applications that truly revolutionize your application management. Now, to check your understanding, what is the primary benefit of using a custom resource definition, or CRD, over a standard Kubernetes deployment for managing a complex application?